Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we are going through a very important as well as an interesting area, namely semiconductors, because without semiconductors there is no electronics, because prior to semiconducting materials we were using vacuum tubes, and as I told you in the last lecture, semiconducting materials are those materials whose resistivity lies between that of the metals and the other case, namely the insulating materials. I mentioned to you in the last lecture there are number of materials which come under the category of semiconductors. Among them, the most important is silicon, the elemental semiconductor, then comes germanium, then gallium arsenide. Very many compound semiconductors are there, and they have wide variety of applications. And in today's lecture, that is lecture number 3, we will have the following as the contents. We will start with the bonding in compound semiconductors. A few comments we made in the last lecture: intrinsic semiconductors, electrons and holes, direct and indirect band gaps which are found in semiconductors, and lastly the motion of electrons and holes in semiconductors. With regard to the structure and bonding, the very important things are, when you are talking about any material in material science, the first 2 things which are to be known are the structure and the bonding. I told you in the last lecture, many semiconductors crystallize in what is called zinc blende structure, but silicon crystallizes in the diamond structure. And with regard to bonding, the elemental semiconductors like silicon and germanium are fully covalent, and when I am talking about bonding, these bondings lead to bands. When you have got separate atoms are separated widely, right, then you will have only discrete energy levels. Only when the atoms are brought close to each other, then only you will be having the bands. The electron densities or charge clouds overlap, they give rise to bands. And with regard to bands, which bands are important? The low lying bands are of no importance. There is a one-to-one correspondence between atoms and solids. The electrons in the case shell is not important, only the electrons in the outermost shells are important as far as atoms are concerned. Similarly, in the case of solids, the electrons in the topmost bands, you know, the valence band, you got a valence band here and a conduction band. Only the electrons in the conduction band and the electrons or holes in the valence band, only these two are important. They only decide the properties of materials. Here we will be concerned about the electrical property, namely the electrical conductivity or the resistivity. And this is the conduction band, you got a valence band. The energy gap, this is called the energy gap or a band gap, and the band gap will be small, as I told you in the last lecture. In the case of semiconductors, it will be large in the case of insulators. Today we will be talking about intrinsic semiconductors. What are intrinsic semiconductors? The semiconductors which are very pure, you take pure germanium or pure silicon or pure gallium arsenide, they are the so called intrinsic semiconductors. We will try to calculate the electrical conductivity in the case of intrinsic semiconductors, which, as I told you, they do not contain any impurity atoms. So, I will be again talking about elemental semiconductors, and of course, you will have the compound semiconductors also without impurities. And at room temperature, the thermal energy of the atoms may allow a small number of electrons to move from the valence band to the conduction band. I told you about what you call the valence band, a set of energy levels you call the valence band, and you have a set of energy levels above that it is called the conduction band. As I will be showing in the slides to come, the electrons in the valence band, by raising the temperature of the semiconductor, by virtue of the fact that they are kept at room temperature, you know, you keep all the semiconductors, your cell phone, everything at room temperature generally, and by virtue of them, the room temperature, the thermal energy is enough to excite the electron from valence band to the conduction band in a semiconductor, because of the fact the energy gap is small. But the same thing is not possible in a insulator, because there the energy gap is much larger. The resistance of these semiconducting materials, they decrease with temperature. Why should they decrease? Because as I told you, when you heat a material like a semiconductor, more and more electrons will leave the valence band and go to the conduction band. They are excited, right. So, the number of electrons you will be having in the conduction band becomes larger. When electron leaves the valence band, it gives rise to what is called a hole. The absence of the electron is called a hole. When an electron is excited, then a hole is left, or there is a vacancy is caused. This vacancy is called a hole. So, in a semiconductor, the conductivity is due to the electrons in the conduction band and the holes in the valence band. Okay. The conductivity is sum of the two factors, the electrons in the conduction band and the holes in the valence band. Both of them ought to be summed up, and the justification for summing up these two conductivities or these two currents also will be discussed in the time to come. As the temperature increases, the thermal energy of the valence electrons increases, allowing more of them to reach the conduction band, crossing the energy gap. That is what is happening. This picture depicts the valence band here and the empty conduction band. When will the conduction band be empty? At 0 Kelvin, you do not have electrons in the conduction band, because all the electrons will be found in the valence band, and because the temperature is 0, you do not give energy to the electrons in the valence band. They are tightly bound to the parent atoms. You take the silicon, all the 4 electrons, valence electron, the number of valence electrons of silicon is 4, all the valence electrons will be bound to the parent atoms. And so, now at this temperature 0 Kelvin, they do not have energy to cross the forbidden energy gap. You require 1.1 eV in the case of silicon, because the forbidden energy gap is 1.1 eV, that is a band gap or the energy gap. So, that much energy should be given to the electron in order that it is excited from valence band to the conduction band. Therefore, at 0 Kelvin the conduction band will be completely empty, whereas at room temperature number of electrons will go. Here in this picture I have got 8 holes. That means, how do you get 8 holes here? 8 electrons have gone, leaving behind what are called 8 holes. For every electron that is going to conduction band, there is an absence of electron, that is called a hole. And so, you got 8 electrons here, that means there will be equal number of holes. So, the important point to be noted down in the case of intrinsic semiconductors is that the number of electrons in the conduction band will be equal to the number of holes in the valence band. The number of electrons in the conduction band and the number of holes in the valence band, they will be equal to one another at any given temperature, because there are intrinsic semiconductors, they do not have foreign atoms, and this kind we will be discussing about N type, P type, where doping is done, and there things will be different. But here in the case of intrinsic semiconductors, the number of electrons in the conduction band and the number of holes left behind in the valence band, they will be equal to one another. When an electron gains enough energy to escape the electrostatic attraction of the parent atom, it leaves behind a vacancy which may be filled by another electron. The vacancy caused by the can be thought of as a second carrier of positive charge. It is also known as a hole. So, in an intrinsic semiconductor, as I told you just now, the number of electrons found in the conduction band will be equal to the number of holes or the number of positive charge carriers, right. A hole is said to be carrying a positive charge, whereas the electron is carrying obviously a negative charge. So, in an intrinsic semiconductor, N will be equal to P. Of course, that should be borne in mind. I will be using it at a later stage when I calculate the intrinsic conductivity. I told you about the energy gap. Now, in the energy band model, we drew 2 lines. You can recall, this is the energy band, right. This is the band structure or the energy bands. They call the valence band and this is called the conduction band. The energy is found along the y axis. No one bothers in general, no one asks what do you have along the x axis. Can you tell me what do you have along the x axis? You have got energy along the y axis. Is there anything along the x axis? I told you just now, if the atoms are far apart, if they are separated by a very large distance, then the 2 atoms will not be interacting with each other, because the Coulombic interaction will be 0, because they are separated by a large distance. This atom will not have any influence on this atom. So, when do you get bands? Only if the atoms are brought closer and closer, the bands are formed. Now, therefore, one should infer or one should expect or anticipate that along the x direction there should be interatomic distance. If the distance separating the atoms, you have got one atom here, another atom somewhere here, then there will be only discrete energy levels. You have got electrons in an atom, you have got the K shell, L shell and so on, right. They are the discrete energy levels. Similarly, you have got another atom separated by a large distance, then this atom will not interact with this atom, there is no electrostatic interaction, then there will be a set of levels here, the K shell, then the L shell, M shell. So, they do not overlap, they do not interact and so on. Only when the atoms are brought close to each other, bands will be formed. That is the important point, right. Even though it is not explicitly given in many of the textbooks, the point to be remembered is along the x direction, along the x axis, you got the interatomic distance. It is not given in most of the textbooks, but the point to be remembered is you should have the interatomic distance along the x axis. Only when the distance between the 2 atoms is decreased, then the bands will be formed. So, you will be having interatomic distance along the x axis, right. That is not given explicitly in many places, but anyway that should be borne in mind. But when you go to a realistic band structure, what I mean by realistic band structure is, electrons are not like cricket balls, right, or football. They are microscopic particles. They are to be dealt with using quantum mechanics. The quantum laws of physics should be applied to electrons, protons or neutrons and so on. Now, therefore, when you apply the quantum mechanical rules, then what you find is instead of the interatomic distance, you will be having k, that is called you got k here, k h bar k is the momentum. The momentum will come along the x axis, and therefore, when I am talking about the band gaps in semiconductors, there are some materials which have what are called direct band gaps, the others have what are called indirect band gaps. At this point, we will have a break and we will resume with the rest of the things after the break. Welcome back after the break, and I told you that the semiconductors like silicon, germanium, gallium arsenide, all of them will have band gaps. Now, the energy band gap that separates the valence band from the conduction band is 1.1 electron volt in the case of silicon, the same is 0.7 electron volt in the case of germanium, and gallium arsenide has got a bigger band gap. Now, when I am talking about the band gaps which separate the valence band top and the conduction band bottom, the band gaps are of two types. One is called a direct band gap, the other is called a indirect band gap. Now, you look at this diagram, this is the band structure wherein the valence band is shown here. Now, the point to be noted is earlier we were showing the valence band as a box, or you draw two lines, you say the valence band, then again you draw two lines, that you call as the conduction band, and that is the way in which you deal with the valence band and conduction band in your electronics lecture classes, and you do not write anything what is there along the x direction also not written, but in principle when you go deep, and again if you want to understand the difference between a direct band gap and indirect band gaps semiconductor, then in such a case you should know what you have along the x direction, along the x axis. Now, electrons being quantum mechanical objects, then when you are talking about energy, the energy can be written only in terms of k, right. The when you are talking about electrons and metals, what Sommerfeld did was he wrote an expression for E in terms of k that goes as E is equal to h bar square k square by 2m, where k is called the wave vector. And so, if you have a realistic band structure, you want to describe the energy values of electrons in the conduction band or the energy values of electrons or holes in the valence band, and you want to explain the band gap, then you should have k along the x axis. This is called a band structure. So, the valence band will be looking like this, the conduction band will be looking like this. So, you have got remember this is the energy axis, and k, what is k? K is the wave vector, it is 2 pi by lambda, h bar k is the momentum. So, you can have energy momentum relation. Now, when you are talking about freely moving electrons, the principal quantum number n does not have any meaning. So, the quantum number like k only will come into the picture, right. The energy can be written only in terms of k. The band structure will be looking like this, the valence band and the conduction band. What you find is the top of the valence band here, this is the bottom of the conduction band. By shining light, you can excite the electron here and make it to go to the conduction band minimum, right. So, you got a valence band top and this is the bottom of the conduction band. So, by shining light, you can excite the electron. This kind of band structure that you have got, it is the semiconductor is said to have a direct band gap semiconductor, right. A direct band gap semiconductor is the one in which by shining light the electron can be transferred from valence band top to the conduction band minimum. This is called the direct gap transition, the electron is transferred, right. Now, on the other hand, apart from a photon which is exciting, you got apart from photon, you got a phonon. You see, the conduction band minimum does not come here, but it is found somewhere here for a different k vector. Now, here you find for the same k vector, right, this is a k space. Now, for the same k vector, right, this is a k vector, right, the k vector will be along this direction. For the same k point, right, you got the electron here and it is transferred to the conduction band. But here you find a particular k point here for which the energy is maximum. There is the minimum in the conduction band comes somewhere here. There will be a band, there may be a band here, the minimum will be somewhere here, right. The minimum is here, the energy difference is large, whereas you got a minimum here corresponding to a different k point. You got a k along this direction, at a different k point you got a minimum for the conduction band. So, this is the conduction band, the minimum corresponds to some other k point. So, you have to apply some photonic energy to make the electron to go from here to here, then some phononic energy will take the electron from this point to this point. So, the one in which the photon energy and the phonon energy both of them are involved, it is called a indirect band gap semiconductor. There will be some heat is involved, right. Phonon means thermal energy is involved. So, a photon energy and a phonon energy, if both of them are involved, that is a indirect band gap semiconductor. Now, at this point I would like to tell the elemental semiconductors like silicon and germanium, they come under this category, namely indirect band gap semiconductors. Now, these band gaps can be experimentally determined, right, experimentally can be determined. I will be discussing about all these things in detail in the time to come, and these are indirect band gap semiconductor. The elemental semiconductors like silicon and germanium belong to this class, namely the indirect band gap semiconductors, whereas gallium arsenide, which is used as a efficient light emitting diode, it comes under a direct band gap semiconductor, right. So, the efficiency is large because it is a direct band gap, whatever energy that is given, it is just taken to, it is used to lift the electrons from valence band to the conduction band. So, gallium arsenide is a direct band gap semiconductor, whereas the elemental semiconductors like silicon and germanium, they come under indirect band gap semiconductors, where the transition is not direct, it is only indirect transition involving both a photon and a phonon. Okay. A direct band gap semiconductor is one in which the top edge of the valence band and the bottom edge of the conduction band occur for the same k point. As I mentioned, at the same k point you have got the bottom of the conduction band and the top of the valence band occurring for the same k point. But whereas in this case only a photon is involved, as I told you, between the transitions, but whereas in an indirect band gap semiconductor both a photon as well as a phonon, both of them are involved in the transition, as the band edges of the valence and conduction bands are separated by a finite k vector, as I showed you just now, that a finite k vector which separates the bottom of the conduction band from the top of the valence band, there is a finite k vector, right, and therefore, this is called a indirect band gap semiconductor. Okay. The absorption threshold, I will show the pictures in the time to come. The absorption threshold for indirect band gap semiconductors, it follows the relation, the given energy h nu will be equal to E g plus h omega. Omega is the phonon wave vector. So, apart from photon, you got a phonon also coming into play in the case of indirect band gap semiconductors. This picture shows it is possible to measure the energy gaps by making light to be incident on a semiconductor. You can have a semiconductor, you got a light source, you make the light to be incident on the semiconductor and you have a detector here, right, and try to find out how much light is transmitted through the semiconductor or how much light is absorbed, it is transmitted or absorbed. So, the absorption can be measured, for this energy there is no absorption, absorption is 0, right. So, the entire light is transmitted through the semiconducting material, there is no absorption, right. The entire energy is transmitted through the semiconducting material, it goes to the detector. You got a semiconducting material here, you got a source here, light source here, and then you got a detector. So, through the semiconducting material, the light coming from the source, it goes through the semiconducting material, the entire light is going to the detector. There is a particular wavelength. What happens is the energy is absorbed, particular wavelength or a critical frequency nu c. This h nu c, what is h nu? H nu is the energy, the photon. This is the critical photonic energy for which the light is absorbed. So, this leads to a direct transition from valence band to the conduction band. What is E is equal to h nu? So, h nu c will be equal to E g. The energy gap will be equal to h nu c, because at this critical frequency absorption takes place. Absorption takes place what? When you talk of latent heat means what? With regard to materials, you talk of latent heat of fusion, latent heat of vaporization. Latent heat means the hidden heat which is used for the transformation of state. Similarly, here when light is falling, some energy is absorbed, means the absorbed energy should do something. What is that? That is being done. The material absorbs energy, or the material makes use of energy, and to break the covalent bond and to make the electron to become free, or to transfer the electron from valence band to where? To the conduction band. So, whenever there is absorption, some work is to be done. What is the work that is being done? The electron is transferred from valence band to the conduction band. The critical frequency at which absorption takes place. Whenever absorption takes place, some work should be done. The absorbed energy should be utilized for doing something. What is that? Is something being done here? The something that is being done here is lifting the electron from valence band to the conduction band. So, the energy that is absorbed is utilized in lifting the electron from valence band to the conduction band. So, that is the critical frequency. Okay. You see a sharp edge here that tells you that the transition is direct. So, this h nu c will be equal to E g, will give you the direct energy gap, right. The direct energy gap can be determined by equating this. E g will be equal to h nu c, E g is the energy gap. Okay. On the other hand, in a indirect band gap semiconductor, the transition is not sharp, right. You see a transition occurring here, and then you have a photon, and then some phonon transition will be there, and so the absorption edge is not sharp, right. The absorption edge is sharp, as is shown here. The photon and phonon transition, both of them will be occurring, what is called the indirect band gap semiconductor. This is the indirect band gap semiconductor, whereas this one is the direct band gap semiconductor. Okay. Silicon, as I told you, is an indirect band gap semiconductor, whereas gallium arsenide is a direct band gap semiconductor. And the important point is, you take cadmium sulfide or tellurium, the percentage ionicity, as I told you in the last lecture, it is quite large. The bonding is not fully covalent in silicon, there is no ionicity. Here, even though they are semiconductors, the ionicity is 69%. The summary of the talk goes like this: bonding in compound semiconductor such as cadmium sulfide or selenium or tellurium, it is mostly ionic rather than covalent. In semiconductors, electrons are excited into the conduction band as the energy gap is small even at room temperature. These electrons leave holes in the valence band. The current in intrinsic semiconductors is both due to electrons and holes. The energy gap in indirect band gap semiconductors is due to a phonon and a photon. Now, let me pass on to the question session. Question number 1: comment on the percentage of ionic character in a covalently bonded solid such as cadmium sulfide or selenide or telluride. justify in summing up of the currents due to electrons and holes. What are direct and indirect band gaps in semiconductors? With this we come to the end of the lecture number 3 with regard to semiconductors. The rest of the things we will see in the lectures to come. Thank you.